have this presentation available. This is the mid-power lineup with the LM28x and the CSP family of devices. When that box opens, so if you would keep your questions available and please mute your phone so that everyone can hear. So, reschedule Monday. I was traveling, wasn't able to get to a landline and get plugged in time, so we just put off till today. We will have another one on Monday where we'll cut our driver lineup and basic wiring. So, this training, very simple, is one is why use this new 2835 package. Second will be what are the new devices in this family of products. The chip scale, and look at what are the advantage of the chip scale packaging and new CSP family of products as well. And then type of design concerns or optic layout design information do we have available on the chip scale. So we'll touch base on that. So I'm going to jump to it. So the 2835. Well, there's a huge market trend we see coming. The 2835 is a very cost-effective package. It's highly used in China. So this allows us to really get down into some really low-cost packaging. We're talking, 3 cents down to the 2 cent level for a typical LED. This is like a S3. So we're literally talking S3, S4 is possible within this year. 2835. That's going to put it right about where we were shipping our LM28x devices at the end of last year. That's how close these devices are to our end products. So you get efficacies up to 140 to high as 170 lumens per watt, depending upon how hard you drive these. But it's really driven by Southeast Asia and China markets. That's just really, really driven, and they're not big concern there on efficacy. So for customers, their big advantage is this is an entry-level type product. So it allows them to go in and offer a product at a very low price point to compete with some of these other companies that are shipping these products in from China. And our projected growth is market share is going to grow in this package significantly, and a good portion of that we predict will come out of the 5630 market share. So the main reason we need to offer this product. Actual portfolio of products. Notice we have quite a few actually, more than I think. 80 and 90 CRI flavors. So you can kind of see some of the rankings there. S2, S3, and S4 are available in the single die. And SASB, that's kind of a grouping of like S2, S3, and S3, S4 type. So don't let us throw you off. It's basically just a wider offering there in the flux rank. So a 82B and the 283 and a 286. So if you're for conventions, you know that the L is for lighting, the M is for mid-power, the 28, the macro dimension of the package, and the next digit is the number of die. So respectively, these are single die, 2 to 3 die, and 6 die devices. And they have a forward voltage of roughly 3 volt, 6 volt, 9 volt, and 18 volt. Also offering for a higher reliability package Zener that will give a higher ESD rating device, and also they go on wires. Some of these lower devices trying to extract every penny we can out of it, so we may not use solid gold wire, but to get their life for DLC premium and things like that, we could offer a gold wire option as well at a high price point. You can see from this slight performance table, but I want to actually go to the next slide. This is our standard marketing slide, so you can actually see that this is a 1 watt class device. The 281 can hit 175 lumens per watt. You can actually push that device up into around 70 lumens at 150 milliamps, and that's roughly around 150 lumens per watt at that point, maybe slightly higher. The 2, it's basically a dual die version of the same one, but even driven at 150 milliamps, you're looking at 127 lumens out of the device. A very, very good device. bulb and amp type applications. The reason for those is because they offer fewer devices are required to match the voltage drop. That's why we have the 9-volt version and the 18-volt version for that very reason. On a standard 2835 footprint, standard SD protection of 2 kV human body model, and it's current of 160 milliamps. Thing, these do meet DLC standard, although they will not meet the DLC premium. DLC premium requires an M90 of 36,000 hours, and low-cost parts just can't hit that. So that's where the 561B Plus and C can fill that gap for the customer. If they need DLC premium, they need to look at those products. The products simply can't hit that high of an L90 number. In order to get there, we'll have to make them more expensive, and then you might as well go to the other ones. So just keep in mind, you can see the offering here in the mass production for the various devices. So then on X Family, we have samples available. We have the documentation on the 281 is actually on the website already. I have preliminary data sheets on all the other devices, so if you need those, send me an email. I'll be happy to send those to you. Now scale. Now, that was quick. That was about 8 minutes. So we're going to forward and talk about the scale. These are function-oriented LED solutions. So we're basically getting down to just the basic materials that are needed to produce light with an LED. So you can see here the lead frame of our standard product, all the different components. You have fill, a plastic lead frame, plastic around the package, and then that will metal lead frame with the die on top and bars because of the structure. You can for our like LM561B had a rough thermal resistance of about 16 degrees per watt. So that actually means so it drives this part 1 watt, which is in this case would be roughly 100, maybe 150 milliamps or something like that. So volts. Get another 16 degree of heat from my TS point on the part to the temperature inside. That's what that means. So 16 degrees hotter on the die, 1 watt. So drive it at half a watt, I'll get an 8C degree increase. What is that? Well, basically it means the thermal capacity of the part. In order for the function, you have to maintain a more heat sinking and have more ways to reduce that heat or limit the maximum temperature of the application. So typically on very high temperature and high lumen applications, they move to something on a ceramic substrate, right? So something we're very familiar, much like our LH351B, you'll see on a ceramic substrate, have the die and then the phosphor film on top and then a dome over that. Still wires, but if it's chip, it would not. So look at our flip chip construction. Our resistance on that package is only 4 degrees Celsius watt. So you can see I drive this much, much harder, even around 3 watts, and I wouldn't even exceed the 1 watt level of the mid-power device for the die. So these are really used in that. Now take a look over at the chip scale, and you can see improvement on this. So they tie directly to the board with a mold around it. So there is no cavity and substrate to enter or to add additional thermal resistance. So it has the lowest possible thermal resistance. And you can get LM101A has a thermal resistance of only 2 degrees per watt. So that said, now I can pack in a lot more of these devices and I can dissipate the heat very readily. I also can put them in a lot hotter environment without having to have as much cost in my heat sink. So what seeing is a design shift mentality in the market. I see people who focused on reducing the number of packages because that's where the cost was, to other new guys looking at it and going, wait a minute, I throw 2 or 3 more LEDs and I'm able to cut heat sink cost in half. And if sink is $1 to $1.50 of my cost, that's a lot cheaper than adding 2 or 3 more additional LEDs. So there's a design shift taking place because of these new lower thermal resistance of these devices. The bottom, we're setting up our lines and our migration to eventually move to silicon-based manufacturing so we can maintain yield and capacity to meet the future demands of the lighting industry. Others aren't doing this, and I'm going to be left with serious shortage and ability to produce enough parts, and I think we're starting to see that with some of our competitors. So the advantage of CSP is the small form factor, and I'll have more detail on each one of these later. But the smaller allows me to pack in more devices. That picture there has roughly 50 to 60 devices on the left. It has over 200 devices, and you can see it's much, much tighter. Once talked about the low thermal resistance, gives heat management, and gives me better efficacy, and really allows a lot more applications to use them. A wide beam angle is another advantage of the chip scale. With the wide beam angle, I can reduce, I don't need lenses anymore to spread that light out. I can even lower my diffuser rating to get because I need as much diffusion in order to reduce hot spots because the LED is naturally throwing the light at a wide angle. Actually, the high reliability, big advantage. No sulfurization issues because there's nothing for the sulfur to bond itself to. There's no bond wires to break, and you're only looking at 2 components with the thermal extension, so that's much more robust design. Form factor, basically we removed everything. You can see from drawing here, this is our typical conventional LED. We got rid of the plastic molding, got rid of the reflector, we got rid of the wire for lead frame. Everything's gone. You're basically phosphor and dye. And you can see the scale of these things. This is scale roughly the size of the 5630, and our arrays are not much bigger than that. So much more light out, and much more finer space, and much better thermal performance. So this is the reliability. We've done sulfurization tests, and you can see where a conventional lead frame, sulfur can bond itself to these and wires and things inside the area, but none of that exists in this package, so nothing to bond to, and we test on that to prove it. The thermal resistance, I put this side in here so you can see here's electrodes here and here on top of the package, and then in between the P GaN and the N GaN, this layer is where all the light is produced, and it has to come out through this structure. And you can see sapphire is actually between. This is where the heat is produced. This is where it has to go through the sapphire to get out of the device. Obviously, over here with the flip chip architecture, here's where the heat is produced, and my electrodes are right here to suck that heat right out and get it out of the die. So it's a much better design. Here's the beam angle. So with the surrounding, hold the phosphor in as we fill it, that with the phosphor mold. And so we actually throw light out of 5 sides on this device. Now, with that being said, obviously I'm throwing a lot more directional light out, so I can have a higher efficacy here because I'm not losing as much light off this surface of this PC board. But this PC board material, the PSR, the photoresistive solder resist, that material is critical because it's in the optical equation now. So light strikes it, it goes back out. So you can recover it, and selecting of that is very important. And we have some app notes can tell some of the guides we're using in like our TVs and things to get maximum performance. into how we're proving this out. So we're working the medicine ourselves and testing it on our own products. So we migrated all our technology and our TVs to CSP now. And we know the benefits of this, and we're already reaping the rewards, and we want our customers to reap that as well. And for us, a big advantage. So I think moving forward, more and more customers need to consider this technology. One is we'll be able to offer future cost downs on this technology, where the older technology will be somewhat limited. But all big advantages in manufacturability and reliability are huge. The arrays and how they differ. So we took a single die from the 101, and we basically do a 4-cavity mold 4x2 and the 9-cavity mold of a 3x3. But that's a continuous piece of phosphor. So light, it takes light out of the whole area. And so in a 30.5 by 3.5 footprint, we have 4 die in series, and that's thus 12-volt device. And we'll operate up to, about 3 watts up to 5 watts, approximately. 3x3 is in a 5-millimeter array, and they're not in series there, so that gives you up to 27 volts, 4 voltage. And these are great single devices that can do an easy R16 or a party type lamp, or par 20 maybe, and with one device in the center, and they're done. So as the LED cost goes down, it becomes more a factor. So your placement cost of each device is important. These allow the placements of 2 to or either 4, either 9 devices with a single placement cost. So when they try to do like a 38 or whatever, they will put down only 2 of these devices and hit that lumen target, as opposed to having to put down 8 individual devices. Tighter element, big advantages in multicast of shadows. So some of these devices, like a PAR MR16, if I have multiple devices, and you can see this in some retail stores where they're in place, just hold your hand near a wall and look at the edge of the shadows. You'll see multi-shadows. That's called multi-shadows. And when that happens, is because the elements have some separation, and there's a line between your hand and each one of the elements. In the very, very small array, we get down to a very crisp. You only have a single shadow, so it's almost like a single point source. That also to lensing. So I have a wide area. My lens has to be much larger in order to accommodate that. And to get the same tight beam angle is very expensive. So LED footprint means much smaller lens to get that same tight beam angle. Building block for us, so they're very simply one of 1, 2, or 9 devices. You can then mix and match and create whatever type of thing. So you kind of think of them as a Lego system. Hopefully, and this is where we get into some of the specs on this. You can see the actual chip size there, and you'll see that the 102 uses a larger. It's actually a multi-junction chip, so you get 2. There's 2 voltage drops inside there, so it is a 930 by 930 die. We have to do arrays of the 102 as well, so that eventually will come out. But right now, this is what we're introducing this family with. So we have the 101, the 102, the 181, and I have a good slide here where it's actually very comparable to our 351B devices, and then the 204 and the 9A. As you see, the actual package sizes are right there, as well as the 4 voltage ratings and the lumens at various currents. And some of these you can drop more lumens or a little less lumens to get their efficacy. We'll be in mass production pretty much everything by May. We're in mass production now on the 101 and 102 by the end of this month. And then 181 and the other high power devices will be May. A question here, can we forward the out on the, yeah, we actually will put that together and be sending that out. Absolutely. So here's kind of the side-by-side comparison again, and I just wanted to show you some of the drive current capabilities. So because of that low thermal resistance, things can be driven very hard, and so you can get a lot of lumens out for very little drive current. So to 500 milliamps, so well above what you could in a mid-power device, but it's going to be priced and comparable to a mid-power type device. The one, for example, 350 to 1500 sounds very familiar, right? It sounds very much like a high-power device in a 35-35 footprint. This is a smaller footprint, though, so you're looking at roughly 1.9 millimeters square instead of 3.5 millimeters square. No substrate involved, very good thermal operation and rays. And it's already designed in for some high bay type applications. So look out for those guys. People are looking for these, and these are very good fits for that. So I'm going to jump through these. These are kind of marketing slides that you can use to talk to the customers on individual ones. It gives you the basic information. That's the 101. The 2, 1, and the 4 and 309 arrays. And so 6 slides there to kind of just talk about performance of these guys. So let's start looking how these guys perform and where do they kind of reside in the overall lumen efficacy range. So these charts kind of here show you where some of our competition might reside in some of their chip scale devices. And you can see where the device is actually performing at a higher efficacy and higher lumen level. And some of our very competitive with many of the 35-35 high power ceramic based devices on the market today. It's right there with them. And then the arrays, we start to get into some of the 3 watt and all the way up to 10 watt type devices from some of the other competitors in the market. Expanding all this, and we'll keep growing family. Definitely believe this is where the future is. And you can see under price per lumen, we can beat the pants off of any of the competitors when it comes to price per lumen. So this device is a great price and has great thermal capabilities. The only downside of the scale is that they need those secondary optics, and they have pre-designed optics on the dome that's on some of these other devices. Then a little bit more difficult because they change their optics to match our device. So right now, no plans to do a dome version of this, but I don't see any reason why we couldn't. But adding a substrate, and at that point, you're practically into a regular ceramic device anyway. So we'll see how it's out, but keep moving forward, and I think you'll find a lot of customers will have a big advantage here. The LH181A to one of the competitor flip chip and to our LH351B. And you can see that we're offering N1 and P1 ranking right at the high level that we're doing with our 351B today. So these devices at 700 mils can really drive a lot of lumens out. And then if you drive them at regular bending current of like 350, you can get some pretty high efficacy numbers as well. So hybrid mix between the two. They outperform the competition chip scale and be competitive with the ceramic stuff. So this is basically breaks it down. Total cost of ownership. So obviously you can see the performance is pretty much across the board the same. When it comes down to pricing is where we actually rule out. The chip scale devices are naturally lower priced. They don't have ceramic substrates. They don't have bond wires. They don't have all these secondary operations. So they are very, very cost effective. And the chart at the bottom here actually shows the lumen per watt versus the lumen per dollar. You can see it's elastic. The chip, the device are very elastic. So the array devices, the 204, and comparing it to the performance, you can kind of see the different flux and efficacies. how to actually lay out in the different scales. So comparing our device to our 351B versus our 204A, you can see it's very similar in performance, and lumen is for pretty range. And then compare that over to like an XPL, so you can actually see how we repair those devices. So we get really, the thermal resistance of the array, and it does have a slight substrate in there to do the bonding of the die, but it's a very thin substrate, just basically to provide the interconnect. And the thermal resistance on it is more like 4 degrees C. Comparing 204 to an XPL directly, so you can actually see the lumen performance for an XPL and on the pricing as well. So the cost total cost ownership is roughly half of that out of an XPL, mainly because of the pricing is more competitive. So 9 array kind of doing the same thing, comparing our 309 to a Luxion M and to an XPH50, so you can see where they actually reside and how well. Now, because there are more die on the substrate, you notice that the thermal resistance of this is 2 degrees C. Some max D rating conditions that are not too bad, and so they can be used in high temperature applications. That people are looking to this street lighting and high bays, by the way. And the chart, you can see where the 309 in a cost lumen per dollar and then lumen per watt performance, we're way ahead because of pricing. It gives us a much lower cost of ownership. And so comparing these devices to COB versus the 309 in a PAR, MR or PAR type application, at 730 lumens and 117 lumens per watt, this is comparing the two applications there side by side. So what the power requirement would be, what the total cost would be for the actual device. And you get in the 3030 mid power is lower price, and the performance is pretty competitive, but you got more LEDs in order to do that. So 309, you put down one part, you're done. So it's right to the COB and comparing them. And that's at 2700 Kelvin, by the way. So patterns and designs, concerns that well, all links right here are all your array files for the 101, 102, 204, and 309. So they're different files, so they can go ahead and start looking at their optical patterns and designs. And then as LAN patterns go, so the 101A and 102A here are the typical LAN patterns. So you can see package dimensions, phosphor wall, where die is, the various electrode pads, and also what the PCB area should be. And then the other corner, I just wanted to throw up there, that's a 042 capacitor. And it'll ask me, well, isn't my CM going to have trouble putting these parts down? Well, if they're using 0402 devices, you can see it's about the same size as an 0402. Matter of fact, the 0402 might be a little bit slightly smaller in some dimensions. So if you can handle that type of device and pick in place, then they will have no problems with these devices. This is the recommended footprint and stencil mask and nozzle requirements for the LA204 array package. You can actually see how the LEDs are laid out, and they're a serial string, roughly 4 LEDs. Now that's really got to be connected on the customer's end. So technically, with a little creative routing, you could do 2 parallel strings of 6 if you wanted to, but most people, they're just doing them in series because that's what makes the most sense. And then I have a slide here which is showing the layout for the H309A and stem mask and everything. So we have a full app note that goes through the whole process, gives them thermal information about packing density of chip scale devices, and I can make that all available to anybody who needs it. So there's in the 181A preliminary data sheet. It is available, and I'm sure you guys get that. The 101A and I believe the 102A information is already on the website, so you can go to the website and get that. But the 181 is a relatively new part, and I have LM80 data as well as the actual preliminary data sheet. That was pretty quick. I went through a lot of information there. I make this presentation available online so you guys can review it or show it to your customers.